Okay, and first of all, I'm talking with your teacher about switching the textbook. I told her this one are really hard to follow. I asked her to print one for you, and she said she need to ask another. She needed to ask her boss, and her boss needs to ask her boss's boss. And the boss's boss's boss. So anyway, um, you need, regardless you got this hard copy or not, I can give you the digital copy. There's no problem. I can do it today after I get back to my place. But even with this book, I'm not faithfully follow any textbook. So you need to. My teaching is a kind of my own. Is my own stuff. So your notes, I still think your notes is your best resources. Okay. I can send you the digital copy of this book. I don't look at it either, actually, to be honest. So you better take the notes. Okay, I can give you the digital copy. Your notes is their best. Today we will continue on vector. So to get everybody warm up, we talked about their geometry last time. So to get you warm up, I was thinking to send you this as a homework, but at the end. What's this mean? Is it off? Is it off? Okay. And now I give you this question right now. So this is just a regular triangle. Okay, just a triangle. Nothing special. Now I want you to prove. A question for me. We proved last time. Say if this is a middle. Okay. I could do it better. Say if this is a middle. We have proved that this and this are parallel. Remember? Understood? Now I give you a question. If here, this point is the middle point, okay? This point is the middle point. Now if the point is not a middle point, if it is a 1/3 point, let's say here and here. Now you prove that, let me label it. This is the middle point, is D, E, okay, this way down. F, G. Can you prove the FG parallel to BC? And the length of this is 1/3 of BC. Can you do that? Using vectors, of course. Can you do it? Can you prove FG parallel to BC? Prove FG parallel to BC, and FG, the length. How to show the length? Anyway, you know what I mean. Is equal to 1/3 BC. Some people use this. The length. Can you do it? If you can, then we warm up now. This is for you to warm up. Proof. FG is a parallel. Two questions. First is this. Proof this. Second is this. So for the subtraction, this is a vector A, this is a vector B. So A minus B is this. Caesar, okay, and let me call it Caesar. And for addition is vector A plus vector B. This is plus. This is a minus. Are you following me? Yes. We need this to do this. Now, if this is a vector A, this is a vector B, so what's here? What's this vector? What's this vector? Yes. Using A and B to, you tell me. Remember, is the second one looking for the first one. Okay, I heard two different. The direction is important. Okay, is the second one looking for the first one? Second one looking for the first one. Okay. So this vector is B minus A. B minus A. This one looking, this one is looking over B, okay? The second one to look for the first one. If my arrow is here, then that is A minus B. Okay. Then what is the vector AF? What is the vector? This is the BC. Let's make it here. BC is this. Okay. Then what is AF? Can you tell me? AF? What is AF? I heard 1/3 A. I only heard one voices. Here, from here to here is A, okay? From here to here is the only 1/3. I said, I didn't write it down. This point is a 1/3 point, okay? This is middle point. This is a 1/3 point. AF is what? 1/3 A. Okay. And similarly, over this side, what is AG vector? What is AG?
1/3 B.
Yeah, good. 1/3 in B. Okay. Then can you tell me what's the vector over here? FG. Yeah, what is that vector?
1/3 B minus 1/3 A. 1/3 B minus A.
So for this vector, it's a Caesar, okay? It's a Caesar. Is this vector minus this vector? Okay? Should I write this? AG minus AF. Is AG minus AF, and we plug in this, okay? So is okay, and we take out 1/3, okay? We factor out 1/3, and is this. Do you see it? Do you see it? And this one is this BC vector. FG is this. So they are the same direction. This is a vector, okay? This is just a part of the same vector. Okay, so they are same direction. So they are parallel. And also show that this is 1/3 of BC. This is 1/3 of BC.
Yes.
Okay. Are you following?
Yes.
Um, can I do it? Can we do it for another one? If it's 1/5 point, 1/5, let's say, yeah, FG HI. HI. Can you prove that HI is a parallel to BC? Do it on your notebook. Do it on your notebook. Okay, suppose you have proved HI parallel to BC by using vectors. I don't repeat it now, okay? If you have difficulty to do it, you can talk to your classmate or talk to me, okay? We have to move on to the second topic, basis vector. Basis vector. Let's say here has a vector called 2, 3. Let's say here has a vector, okay? I will give you time to copy it down, this plot. Let's say here has a vector is 2, 3, okay? And uh, this vector, you can look at it as the two vectors. You can look at it as 2, 0 plus 0, 3. You can dissect out. You can look at it. This vector is 2, 0 is this vector, okay? 2, 0 is this vector. Agree? You need me to draw it with a color. Okay, 2, 0. 2, 0 is this vector. 0, 3 is this vector. Zero, 3 is this vector. You see it? 0, 3. This one, I always want you, we are two fingers pointing at the same moon. Okay? Two fingers are pointing at the same moon. This 1, 2, 3 is the same as this one. Okay? 2, 3. Okay? 2, 0 is the red one. 0, 3 is the blue one. There are two fingers pointing at the same moon. Okay? Don't do one thing and forget another. So the same vector, you can look at it as a two vectors of summation. Remember how to do it? 2 plus 0, that's a 2. 0 plus 3, that's a 3. Besides, you know how to do it in this way. You need to know how to do it in this way. Okay? And this is can be expressed as a 1, 0. This is a 3 and a 0, 1. 1, 0? Where is the 1, 0? Where is the 1, 0?
1, 0, left, right.
Where is this vector? I make it thicker. This one is a 1, 0. This one is also 1, 0, okay? Okay? Not necessarily starting from 0. Many times we don't care the origin. We don't look at here. We don't need the origin. We don't need the origin. This is why this and this A and this A are identical. And where is 0, 1? Where is this vector? Where is this vector?
Vertical 1.
It's here. I make it thicker, okay? This is a 0, 1.
Alright.
So this is the whole thing, the basis. The basis. This one is the basis. This one and this one. 1, 0 and 0, 1. Are the basis. Okay? It's like when we are talking something says 3 kilograms. We have a base. What is 1 kilogram? Okay? We need to know what is 1 kilogram. Otherwise, 3 kilograms doesn't make sense. Okay, so these are the bases, and we have a spatial symbol. This is called E1, elementary. E means elementary. They have the name elementary. Okay, and this is E2. This is E2. This is E2. Okay? And we can keep writing. So this is equal to 2E1 plus 3E2. 2E1. So here 2, 3 is 2E1 plus 3E2.
What's that A for?
E2. E means elementary. And elementary. This is the basis vector. We're kind of now we are doing dissection. Doing dissection. We are this vector. We are going inside. Oh, it has the components. This vector. There are 2 copy of E1, 3 copy of E2. This vector. We need to understand a vector can be we treat it as the 2 vector summation. Okay, we can dissect the vector.
Yeah, of course.
All right.
Come on, you reply.
Okay, we can take a break now.
Okay, 谢谢老师。
Stop. A vector can be look at the components. A vector has a components. This is what I'm trying to say. Okay, and everything has a components, right? Yeah, air has oxygen, has a nitrogen. Um, um, this kind of stuff. Okay. Um, um, like a medicine, inside has various components. This kind of chemical, that kind of chemicals. For vector here, it also has a components. The basic components, like vitamin A, vitamin B, vitamin C, they're put together. They will say, oh, this is a pill. This is a pill that has several vitamins in it. Okay. And this question we have talked before. I want to go through a little bit. This is a river, is flowing, and the river is flowing, and the vector is a 2, 0. Okay, is 2, 0. This is the water is flowing. Say that the origin doesn't matter. No matter where you are, no matter where you are in the water. Yeah, if you cannot do the question, you can ask her. She was in my linear algebra. That no matter where you are, you are hit. You are hit by this vector. Okay, to 0. Now, I want you to give me that you have a boat. You have a boat. I want you to go straight. The question is, how the boat go? How the boat go? How the boat go?
Something like this.
Okay, let me say, if your boat is to go this way, if your boat is to go this way, and this vector is minus 2, 0. Your boat is the opposite direction and the same speed. So what's the final result? What's the final result? What's the final result? What's the final result?
0.
Then your boat is not going anywhere, right? Your boat is just hold there, not pushed away. It's just enough to be still inside the river. It's not going that way. It's not going up that way. Okay. Now, if your boat is going and not now, I need to. The first one is this much, okay? The second time the second one is this much. Is minus 2, 1. Okay, your both is minus 2 and 1. Is this one, okay? So what's the result? What your boat is doing? What your boat is doing? What your boat is doing? What's a boat? 0, 1. Okay. So the final result is your boat is going the final result. Your boat is going straight, but with this much speed. Is going straight, but with this much speed. You can look at this, the components. You can look at this as I copy down this. I copy down this. Now this can be two components. Okay. So one is minus 2, 0. And one is 0, 1. The two form this. And this part cancelled, this part cancelled the water strength, water force.
Yes.
Okay, this part cancelled. They are just exactly opposite. Exactly opposite. And the same length. So the leftover is this one. The net effect is this one. Okay. Are you following? Are you following? Now, if your boat is going this one, let's say is a minus 2 is still when you project to horizontal is still minus 2. Yes. What do you mean? Huh? Yes. So the two cancelled each other. And only this one left survived. Only this one survived. So, okay, now the third scenario. The boat is going this direction. Is a minus 2, 5. Minus 2, 5. Okay, this one, minus 2, 5. And now you can look at it, I'm out of space. Now you can look at it as this is the water force. Okay, minus 2, 5. You can look at it as a minus 2, 0. plus 0, 5. So this vector, you can look at it as the summation of this one plus this one. Can you see it? This one is the summation of this one plus this one. Parallelograms. The vector A plus vector B. Parallelograms, okay? This is also the summation. This is also the summation. Okay?
Yes.
And for here is a rectangle, is not just a parallelogram, is a rectangle. A vector can be considered to be, this vector can be considered as this vector plus this vector.
Yeah.
Like this vector can be considered as a 2, 0 vector plus 0, 3 vector. Now we look at this one as a two parts. Why we want to look at it as these two parts? We want to look at it as z, the component in that direction, and the component in that direction. And this one and this one cancel out. The final result is we are going straight and it is faster. We are going straight. This one is going straight and is faster than that one. Please copy down please write down the board. Yeah. Okay. Okay. Now this is a review of a live application. This is one example. And let me say another example is everything has a gravity, right? Everything has a gravity. This one, a box, whatever, it has a gravity, which is a vector. Let me say it is a 3 kilograms. Let me say it's a 3 kilograms. Now a helicopter, let's say a helicopter is holding it, give it a force. Give it a force somewhere. My question is we want to, this one move, not go down, not go up, move horizontally.
Yes.
I want you to tell me what is the force, which is this vector, the force. What the force should be like. If this, let's say this is 0 minus 3. Minus means heading down. Okay, means heading down. Okay. What's this one should be? What's this one should be? What's this one should be? We can look at it as this one we want to find out. We can look at it as a two components. We can look at it as a two components, like dissecting out, So this one should have this one and this one should be just the opposite, to compensate, to cancel out this one. Okay, so what it should be is 0, 3. Okay, so this one canceled out.
Yes.
And here, this one will be the net effect. If this is a 1, 0, what's this? What's this? Huh? So there are two components, 0, 3 plus 1, 0. So what's the result? 1, 3.
Yeah.
Is a 1, 3, okay? So the helicopter dragging it is the force. If it's this, all these are the same level. Let's say this is 5, 3. Let's say this is a 5, 3. This is a 5, 3, okay? Then it can look at it as a one component is this. One component is 0, 3. And another component is 5, 0. Okay, this one can look at it as two components. Okay, and when we add the gravity, the two canceled out. These two canceled out. The net effect 5, 0. So will be what we saw if the helicopter is dragging this box in that one. We saw it is the net. We saw it is going horizontally and going faster than before. Please copy down this. the most important theorem in the world. Yes. Is the most fundamental theorem. And you will see a little bit later. Do you know what it is? What is it talking about?
Biology.
A right triangle. A right triangle. The hypotenuse, this is called the hypotenuse, right? C squared equal to A squared plus B squared. I'm just ready to talk about the most important theorem, and some student just left. Okay, the A squared plus B squared equal to C squared. Okay. If this is a 4, if this is a 3, what's here?
This is 47 square, 49. No.
Okay, that's it. And this they call this 3, 4, 5 as a Pythagorean triple. Pythagorean triple. And there's another one, 12 square plus this is 13 square. Is this correct? I don't remember. So this is 144. Let me check. 144, 25. Yes. Is totally is 169. This is 1. This is 169. This is 169. Okay. Do you see it? This 12 square plus 5 square. Do you see it? And it's a 30 square. You can check it. Let me talk about this first. 5 square. 5 square, okay? Let me show you. Let me say I'm 5 feet. 5 something, okay? From here to here, 5, right? Now if I'm lower, that's a 4, okay? Here has anyway a person or a stick, whatever. 5, okay? Now this is stick. Here is a 5, okay? Now here is a 4. The stick lower, because it's the same stick.
Yes.
So what's here? What's here, man? 5. It's the same stick. It's the same stick. Okay? 5. Okay, now I lower. I'm still 5. Okay?
Yes.
Here is the 5. Now here is the 4 to the ground. Is it? How much is here? How much is here? How much is here?
4.
This is a 4. Here is a 5. Here is a 4. What is here? What is here? 3. Okay? So here is the 3. The red part. Huh? Why is the 3?
Because it's 3.
I said in the beginning here is a 5, okay? Here is a 5. Now I'm 4, okay? 4, okay? I'm still myself. I didn't become longer, became shorter, okay?
Yeah.
So I'm still 5. So from here to the ground is a 4.
4, yes.
My feet to the wall is a, what's the distance? 3 is a 3.
3, dude. I told you. 3.
3. Huh?
I get it.
This is
I do, man.
this is me, okay?
Yeah.
5. 5, 4, 3. This is the. I said I'm lower. Here is the 4. Let me do. Let's say this is a 5.
Yeah.
Okay, now I'm lower. In the beginning, here is a 5.
Okay.
Now I slide down. Now this is a 4. And this is still 5. Because this is the same state.
Yes.
Same state. Here is a 5. Okay. Now I'm lower. Okay. So here to the ground is a 4. This is a 5.
Yes.
And from here to here, what's the distance?
3. We don't know.
Is a 3.
It's 3, man.
Yeah, yes, we don't know it's X. It's X.
I don't know, but it's 3.
It's X. Right. It is. Do not know. But Pythagorean said. Yes. Pythagorean said 5 squared plus 4 squared plus, we don't know, plus this are equal. Okay? This square plus this square equal to this plus this. So we can find out that this has to be 3. This is a 3. Okay. This has to be 3. Now the amazing part is here we only lower by 1 unit. Originally is a 5 units. Now we lower by 1 unit. But this end only moved 1 unit. But this end, how much moved? 3 units.
3 units, yeah. I told them.
3 units. It's a 3 times. Here you just lowered by 1 unit. But here you moved by 3 units. This is amazing. Here again, you lower same state. You lowered by 1 unit. But this end traveled from here to here, which is, this is a 3. This end traveled 3 times. 3 times of this end. This end traveled only 1. Okay. So when we ski or boating, you see those people, they push the boat.
Yes.
The state one, they only lowered by 1 unit, but this end pushed the boat
As long as it's
3 times longer than how much you move.
of course.
Okay? And for example, if this is originally is a 13 unit, this is the state is a 13 unit. Okay. Now if my state is moved or pushed that way to be easier, so 13 becomes 12. Here is the 13. If I lower the 1 unit, how much the state length is still same, do not change. You push it, your state didn't become shorter, didn't become longer, okay? Or in the beginning, your state is vertical. Now you pushed a little bit, you lower. How much is that?
5.
It's a 5. Here you only lowered by 1 unit, but you the other end traveled by 5. This is unbelievable. This is unbelievable. Those people ski. So he just lowered a little bit, but he pushed longer. And for you guys, like the train, Pythagorean is everywhere. Let me finish this, okay? Your two wheel, okay? You are connected by the stick, okay? So when it's lowered, when it's turning, and let's say turn it over here, and this is pushed further. You will hear this part just lowered by this part, but this end just, but the other end is traveled longer. Is longer. And why our world, why this happens, is really amazing. When we walk, actually, it also has a Pythagorean theorem in it. We lowered a little bit, but we pushed further. It's just amazing. If we lower a little bit, but the other end pushed more, we walk. We lower a little bit, we pushed more. Why accidentally? Is this an accident or is it some grand design? I left to you. You want to do philosophical debate and whatever. Okay, we stop here. Four. Okay. This is a right triangle. Do you see it? This is right triangle. Right triangle. What's the length of this vector? What's the length of the hypotenuse? What's the length? Is a 5.
Yes.
Okay. So the norm is the linear algebra term. Anybody who had the linear algebra class knows also it means the length. It means the length of the vector. Means the length. Okay. We said the vector has a direction. It has a length. The length means how large it is. Okay? It is the norm. So, for 2 dimension, here I keep using only 2 dimension. Only 2 dimension. But it could be 3 dimension, like in this room, 3 dimension, right? Could be 4 dimension, could be 100 dimension. But let's say for 2 dimension, let's say this is a vector. I cannot do the vector v. Let's say this is a vector v. Okay. Vector v, this is a number. This is another number, okay? Could be A, B, okay? The symbol, the norm, the symbol is 2 bars. 2 bars. And the length, if this is a, this is a B, the length is a squared plus b squared, and take a root, take a square root. Copy down, okay. If the vector is 3 dimension, if the vector is a 3 dimension, A, B, C, the length or the norm A squared plus B squared plus C squared. The length in elementary school, when we say number 3, it is here, okay? When we say minus 3, where is the minus 3? It's here, okay? But the absolute value, what is absolute value? Absolute value is its distance to the origin. From here is minus 3, but the distance from here to here is what? Is 3. Okay. When you take absolute value, then we throw away which direction. This is only one dimension. This is only one dimension. It's only forward or backward. The absolute value we throw away. That if it's 3, what's its absolute value? What's the absolute value of 3? It's the same. Absolute value 3, and it's also 3. Minus 3, absolute value is also 3. Because the absolute value is talking about the distance. It's talking about the distance. The norm is also talking about the distance, the length. And we are throwing away the direction. We are throwing away the direction. Okay. We only get the number, which means the length. We do not know is pointing that way or pointing that way. We do not know. Okay. Sometimes we only want to know the length. Sometimes we only want to know the length. Just like in elementary school, in some scenarios, we only want to know the absolute value. In some scenarios, we do not care is it forward or is it backward. Okay, this is the norm. That question, that Pythagorean question, let me bring that up again. If this is 4, 3, okay, this is what? 5. Okay, has a board. This is a flat on the blackboard. It's a 2-dimension. Now, I'm pointing it over here. Now it's a 3-dimension. Okay, point out here. And this is a 12. This is a 12. This is a 2, 3. Imagine this is just a line. Okay, this is a treated as this 1 inch as just as a
1 line.
Ball line. Okay, I have a stick over here. This one and this one forming another triangle. Do you see it? Just this triangle is not flat on the board. Now one side is this, another right side is this. Let's say this is a 12. Let's say this is a 12. Then what's the length from here to here?
12.
From here to here.
12, 13, 14.
Yes. Well, from here to here. Yeah, this is a, here has another right triangle. One side is a 5, another side is a 12, 13. I drew it here, that was a 12, right? Right? And you told me this is a 13, right? Yeah. Imagine I use a piece of paper. Yes. I draw this as a 2 triangle. Okay? Now I fold it. I fold in this line. Here has a, okay, here has one line, one triangle, another triangle. Let's say I cut it in this line. Now I make this side vertical to the blackboard. Vertical to the blackboard.
Also the longest side of...
Longer side, let's say, is here. Okay. Yes. Because I didn't cut, I could use a scissor to cut in this, or use a piece from the, for those shipping, the package,
Yeah,
those board. Let's say I cut it that, and I turn this. I turn this part up. This part still I hold it on the blackboard. This part I turn it up. Okay. So doesn't change anything. Doesn't change anything. 13 is 13. It is just folded by me. Okay. So in even though 80% of time in this class we are talking about only 2 dimension. We are talking about 2 dimension, which is a flat. But you should realize everything is can be applied to 3 dimension or 4 dimension. If this is a 4 dimension, A, B, C, D, okay, in A, B, C, D, and the norm will be A squared plus B squared plus C squared. And what?
D squared.
Plus D squared.
Yes.
And then take the square root. Take the square root. Okay. This square plus this square, 5 square plus 12 square equal to 13 square. Okay? 5 square is what? It's a 3 square plus 4 square. You see it? Okay, we are traveling backwards, which originally we starting from here and built the second right triangle. Let me talk about from backwards. We talk about the second triangle first. 5 square plus 12 square equal to 13 square. And this one, this side is the right side for this triangle, but is a hypotenuse for first triangle. Is the hypotenuse for the first triangle. So 5 square equal to 3 square plus 4 square. Okay. So we plug in, it becomes 3 square plus 4 square plus 12 square equal to 13 square. Equal to 13 square. thing is even though we do not know, let's say we do not know, this is the x. So this is the x. Here is the x. Five square plus 12 square equal to x square. Okay, 5 square equal to, so is x equal to z. Let me raise one example. In this room, let's say from here to that projector, from here to here, let me say, how much I should say? Let's say origin is this corner, okay? Origin is this corner. And the vector is from here pointing to that projector. And let's say from here to here, to make our life easier, okay? That's a 3, okay? And from there to here, that's a 4. Okay? And this one, let's say, is also 4. Okay? This one is also 4. Are you following me?
Yes, love.
So it's a 3,
Yes. 4.
4, 4.
4.
Can you tell me the length from here to the corner?
33, 4.
Yeah. Can you tell me the length?
Yes.
You have to use the Pythagorean twice. So this is a 3, that is a 4.
And then
So let's say I'm right on there. From this point to the corner, what's the length?
4.
No.
No. This one is not square.
From the floor, this point.
Okay, this one is 5. Why did you do that?
This is a 3. This is a 4. Okay? And I'm asking you from here to the corner, what's the length?
5.
It's a 5.
5. Yes.
3, 4, that is the hypotenuse.
Yeah.
From that point to that is a hypotenuse.
5.
Is a 5. Okay?
Yeah.
And now forget that from there in the middle air to that. So that's another triangle. Now this triangle is left up.
Yeah.
So this is a 4.
Yes.
This is a 5.
Yeah.
So from here to there, what's that? From the corner to there.
6.
It's not it's not a clear number.
You can think of it as 6.
This is a
Square root of 41.
5.
5.
This is a 4. What's there here to there? Now this triangle is lifted up. is lifted up. Hypotenuse, that's hypotenuse. From here to there is one right side. From there, go straight up. Is another right side, okay? So from here to over there, what's that? How long? From the corner over there, how to calculate from the corner here over there? How to calculate? That's the first right angle. 3, 4. Got it? So from here to there, on the floor, okay, is a 5. 5 and the vertical is a 4. So 5, vertical is a 4. Here is the projector, okay? Here is the projector in the air, okay? So what's here? What's here? So it's a 5 square plus 4 square. Okay. 25 plus 16. 41. It's a 41. It's a 41. So it's from here over the projector is the distance is this. Is this. And this 5 actually is a 3 square plus, so it is 3 square plus 4 square plus 4 square. Because 3, 4, 4. 3, 4, 4. That one is 3, 4, 4. The part is a 3, 4, 4. And the distance from the corner over there is the norm of this vector. Is the norm of this vector. Length, norm, length, length. So for three dimension, one example is the color. In computer science, you see, nobody's screen is black, white. Everybody's screen has a color, right? Beautiful color. So you can see the picture, you can watch the movie. And every pixel, let's say this is your computer screen or your cell phone screen, okay? Actually, is many pixels, you know, right? Yeah, many pixels, many pixels, right? And why here is, let's say here is a flower. Why each pixel, the column has three numbers, has three numbers. It's a three dimension. It's the red, blue, green. I think it's the red color, blue, green. R, B, G. That's right. Red, blue, green. So each dot, each pixel, it is defined. It is what kind of color it is defined by the three numbers. Is defined by the three numbers. And the numbers of value is from 0 to 255. So there are 256 choices, possibilities. Okay? The first number has 256 choices. So by mixing you got different color. Some is dark, some is purple. By mixing the color, okay. They want to, if you want to write some computer programs for testing, be quiet, okay? If you want to, like I have seen some programs in the cell phone, you slightly short the one and ask you, see, can you see it? Yeah. And very faint. This has a background, and one. So let's say this dot and the background dot. So if this is a one background 166, it is not dark, okay? Let's say some kind of color. They set the background in some kind of color. They think that background is comfortable to human eyes. I don't remember. Let's say this is a background color, okay? You can adjust on the, you can type in the three numbers, see what color it is. It's a mix. This defines the red. This defines the blue. This defines the green. Three kind of component you mix, you get complete. And you want to design, you want to hear slightly different from here. Okay? And some people say, I cannot see it. Then they say, okay, can you see it? Then you move on to the next level. Make it more, the contrast is bigger. And some people say, oh, now I can see it. And some people say, no, I'm sorry, I still cannot see it. Then they move on to the third, now can you see it? They make it more different. Yes. Now they say, oh yeah, I can see it. They say, oh, your eyes are bad. You watch it too much. So it's for testing. It's for testing the people's eye, the health. Not colorblind. That's a different story. Okay. So let's say this is the background. your first test. Here, this pixel is just slightly different from the background. So this is a vector. This is a vector, okay? For the first time, you want to make another vector in 3 dimensions.
Yeah.
3 numbers. You want to make another one. The difference is very, very small. The difference is very, very small. Let's say you made it 164 and 76 and 211. This is a background vector. This is the one standing out, but it's very faint. Only very healthy eyes can saw the difference. And they can say, oh yeah, that's 1, that's number 1. Most people maybe say, no, I cannot see it, it's still same. Then you move it larger. You can say, okay, you cannot see it, I make it the distance. This is the background vector. Let me say B, background, okay? This is the first. Let's say A1. And this is A2. And so let's make it 70. And this is 198. Now this vector is here. The distance from the background to here is longer. Okay. Now you this kind of color, this pixel, sure? Can you see it? And maybe you have people say, oh no, yeah, I can see it. Another half is, no, I still cannot see it. Yeah. And they have to make it even larger, the distance even larger. So, wow, the eyes are so bad. And now it's 100, and it's 50, and it's 112. Okay, so the difference, the two vectors, the background, and this is the one, the picture. The difference is very long. Now it's, oh, no, yeah, I can see it. It's 1. Wow, this is a large difference. I have seen APP for testing people's health. Eyes healthy. Yes. So by calculating the distance, this is a very subtle distance. If you can see it, oh, good eyes. And this is the middle distance. If you can see, oh, it's a circle. Yeah, I see it's a circle. Then okay, your eyes are okay, not great, but not too bad. Some need that. This is much larger. So we are calculating the distance. That's the norm. That's the norm. The vector, this vector minus this vector, get this vector, right? And we calculate its norm. And this vector minus this vector, get another vector. We calculate its norm. The length is the norm. The length longer means it's more different compared to the background. Okay? It's longer means the contrast is larger. So you can write a program in 10 levels. In 10 levels. I just draw 3 levels. 1, 2, 3. You can write it, can you see it? Can you see it? Can you see it? And the testing people's eyes. So Pythagorean is in many places. We didn't realize it. Okay, we take a break, a short break. Okay. Pause. Red, blue, green. Red, blue, green. You can see instead of we say, oh, red is what blue, we say it's a vector. Vector. Now advanced format. Advanced format. And it's clear. And it's also easier for us to compare this color definition with this color definition. It's easy for us to compare. By calculating the distance between two vectors. By calculating the distance between two vectors. You can see the vector is useful. There. Now we move on the dot product. This is some vector times another vector. So when we have a vector 1, 2, dot product 3, 4. What's the answer? No. I don't. Even myself do not know. So I should not write it down. I don't know. But say you don't know how why you are teaching here. I know the meaning. I do not know this. Okay. So what's the meaning? Dot product is dot. Okay. First of all, look at that. If this is this, completely different story. Completely different story, okay? Cross product. We are talking about dot product. It's very beautiful. I love it. Why? Why I love it? Because this is used in love match. These days is popular. People write some platform to match the boys and the girls. See, and how do they find this boy and this girl match each other? Is by using the dot product. Yeah, you will see today. And you can write a computer program now to. I do not want to do that for you. I have a more important thing to do. But I can tell you what's going on inside. How can you find this one is match with this boy match this one better instead of this one match with another girl.
Like getting website,
right.
Application.
Yes. Why? Let's say A and B are boys, C and D are girls. Okay. And you need some mechanism to find A and D is more
Better.
Match better. B and C match better. You need some mathematics inside. Not not blindly say, oh, maybe you can try A, or you can try C, or you can try D, or you can, because there are hundreds, let's say there are hundreds, or even thousands, if you are a big boss. Thousands. How can you match this one with that one? How can you match this one with that one? They're using vectors, okay? They're using vectors, you will see. So what is a dot product? Dot product, let's say here is the vector A, okay? This is the vector B. Right now it's a two-dimension. It's a flat, two-dimension. This is the vector A, and this is the vector B. And vector A and the vector B dot. What's the meaning of that? The meaning is, this vector A pointed there. This vector B is pointing somewhere, another direction, okay?
Yes.
This could be one person. This could be another person. They have a different personality. They have a different hobbies, okay? But there's some overlapping. Look at the B. You can look at the B as two components, like I said in the beginning. It's two components. It's B1, you can say, and you can look at this is the B2. You said this B is a B1 is a B2. B1 plus B2 equal to B. Do you see it? A vector always can look at it as two components. One component is here, another component is there. This vector this B can look at it as this B1 plus B2. Okay, this is B1, this is B2. B1 plus B2 is B. Do you see it?
Yeah.
Do you see it? The river, the crossing river. Did I say that the boat you can look at as two components? One component exactly just cancel out the water flow, and another component, the component goes straight, crossing the river, right? Right?
Yeah.
So why everybody keep quiet? I'm not going to introduce Joe. I'm introducing dot product.
Oh my God, Lashi, we are interested to hear about
It's on the YouTube. So this component, this vector is one is how similar with A. This B1 is similar with A. Okay. B2 is vertical to A, which is absolutely no common interest to A. This part. Let's say this is a boy's choices, personality. Let's say you you ask the boys the question, do you like music? And he say yes. Do you like sports? Yes. Do you love dancing? No. Do you love reading? He say yes. And okay. And you can ask more. Okay. And you ask the girls, and do you love sports? No. What's the second one? Music?
Music.
And they said yes.
Dancing.
The dancing, he said yes. Do you love reading? He said yes. And so, in these girls, there are two different vectors. Two different vectors. However, this vector has some similarity as A. It's not completely similar to A. If it's completely the same direction, there's a little bit similar and a little bit absolutely opposite. Okay. So this vector, the how much similar is z here, is z here. And if another vector is like that, then this vector as on this direction, on A's direction, longer, right? So this person is more similar to this person, right?
Yes.
Compared to the two persons. This one and this one has more common interest, more similar. Okay? And this one and another person, if like that, and you project is so for this person, most part is over here. Most part is over here, which with A has no any common ground, and just a little bit common interest.
Yes.
So if you want to introduce, let's say 3 girls and 1 boy, you want to introduce this one, you say, oh, this one is more match with you. Okay. And to do it, we use a dot product. The dot product is, you find these, that you project to this direction. You find that. How to find, this is let's say this is the theta. Well, here is the theta. Okay. So A times B is the result is a number, it's not a vector anymore. It's no direction anymore. It's a number, okay? So it's B this is what's this? This is the norm, okay? This means the length could be here. I'm using a general. I'm giving you the general formula, okay? This is the theta is the angle between the two vectors. Theta is the angle between two vectors, okay? So the B, do you remember cosine theta? Yeah, let's say here is, I'm reviewing trigonometry. Theta. This is the B length. This is the B length. And what's here? What's here? Is this length times the cosine theta. times cosine theta. This length times the cosine theta is the shadow. Look at the like a sunshine projecting from the head. Okay, a stick. You have a sunshine project, and how long your shadow, how long the shadow is your length, your stick length times the angle cosine theta. Cosine theta. This side is what? This side is what? Is times sine theta. Let's say if this is a 1, and this is the angle, this is angle, then here is the sine theta, here is the cosine theta. Here is the cosine theta. When this is a 1 unit, then here is the cosine theta. Here is the sine theta. If you find a girlfriend, you need to get this correct. Trigonometry. So, is this length times the cosine theta. So you got this length, okay? This length times the u. Let's say you are A. Your personality, you are vector A, okay? You have some choices. So another person, this one maybe looks clear, projecting, one part is how much is similar to you, another part how much different, very different from you. So this part is the similar part to you times your length. That is the dot product. That is the dot product. To write it in a better way is you can put a b in front and the cosine theta in the very end. In the very end. So the dot product is this one's length times this one's length times cosine theta. Theta is the angle between the two. This is the formula. You need to write it down. This is the dot product formula. We need the. Are you following me?
Yes.
The meaning, okay, the meaning is that you're calculating, basically the dot product gives you how similar the two vectors it is. If the result is larger, means, oh, the two vectors, they are kind of similar. If the result is very small, you say, wow, even though like the color, wow, they are very different. One is pointing there, another is pointing another way. It's very different. The more similar the dot product is larger. Is larger. Some special cases. If the two are same direction, so the theta is zero. It's zero, right? The two is zero. Cosine zero is one. Is one. Okay? So when two are overlapping, this is A, this is B, okay? So for this, B is equal to the length, this length times this length. You need to write it down, these special cases. Special cases. Theta is zero. Theta is zero. Is so is this length times this length. Okay, this is one case. Another case is when A and B are vertical. A and B are vertical. Nothing in common. Nothing in common. This is A. This is a B. The theta is 90 degree. When theta is 90 degree, this is zero. This is zero. Yeah. So something doesn't matter, times zero is zero. So another case, another very important case. This is a very important because it's used 90 degree. When it is 90 degree, the A is a number zero. It's a number zero. So if a two vector dot product is zero, you can go backwards. You know the two vectors are vertical each other. They are vertical each other. If you know the two vectors are vertical each other, you know the dot product is zero.
Yes.
You know the dot product is zero. And for this, in the beginning, the reason I cannot give you the result because I can calculate this vector's length. I can calculate this vector's length by hand. And it's hard for me to calculate the two vectors angle. The two vectors angle. Okay. For computer, then they have you just type in then immediately give you the value. Immediately give you the value, the dot product. Is not 1 times 3, 2 times 4. Is not. Okay. Just like you want to check. Let's say they have the database, different person, different girls, each one's the interest, hobby, and they will say which one kind of, and you give your result, you give your like, what you like. Uh, uh, um, and use their computer this one times this one dot product. You don't you don't even do it by hand. This vector times this vector dot product is what. Computer immediately do it and do it for you, do it for you, do it for you. Let's say there's 1,000 in the database. And they find the largest um, the largest the dot product, and they say, oh, this one we recommend this girl is similar to you, and and this is one way, and another way. These days, the face. They take a picture, immediately recognize who you are, and they find now it's getting more and more everywhere. You can pay by, you don't need to give the password by putting the picture. But how do they saved your picture in the database? They saved your, but how do they know? Let's say last year they have your standard picture in the database. Now this time you go into the store and you want to pay the money by taking a picture of you. How can they match? There's a thousands picture, hundreds of thousands picture inside the database. How can they immediately recognize, oh, that's you, this is you? It's also by the similarity. It's this is just one dimension, just the interest. For this, then is basically the same. Basically, is the same. Is just this is just one. This is the many vectors. The many, and they find that these ones dot product is a database. So this is John. They immediately recognize this is John Smith. And so it's unbelievable. They are doing it unbelievably accurate. Unbelievably accurate. For anybody in Yunnan, I have checked. Is in police. They just in less than 30 seconds, immediately find out what's your name, where you have lived, your original picture. Is for the one I experienced in the demo is only in the Yunnan database. If the resident of Yunnan, they say, I'm not a resident in Yunnan, so I'm not, my friend my friend, even you cover something like glasses, like maybe you put a hat, they immediately find out. Doesn't matter. You with a hat, with a glass. Let's say the picture in the database, no glass, but today I wear glasses, no problem. No problem. Um, it's unbelievable. Here is the simple case. You are matching two different people. Here is more advanced, but is built on top of this. Um, I think that's for today. You may stop here. Um, trigonometry.